All right, in this set of videos, we're going to be talking about Euler's method, which is a way that we can numerically generate solutions to differential equations without knowing how to, like on pen and paper, write down those solutions. So it's another way for us to understand differential equations before we actually start solving them. And that's why I like to cover it at the same time as we do direction fields and equilibria. So we're going to start off talking about intuition for how Euler's method works and sort of what it does. And to do that, I'd like you all to think back to direction fields. So I'm going to draw a little example real quick. So suppose we've got this direction field. Just accept that that's what the direction field looks like. At some point we sat down, we drew a bunch of arrows, and we got that direction field. And then for some initial condition, we learned to follow those arrows and get a solution. That's what we learned to do when we covered the direction field section. And so what we did was we plotted solutions for any initial condition. X0, Y0, by starting from that value, and then following the arrows. So that's what that process was. For a given initial condition, we followed the direction of the arrows, and we generated an approximation of the differential equation. This is related to linear approximations like you would have covered in calculus classes. Where sort of think about, this would have been for x and y, this is for x and y. Going backwards a little bit, when you had some function, y equals x squared plus 1, you learned how to, at a point, compute the derivative, which gave you the tangent line approximation, where like the slope of the tangent line is the derivative, that line. And making the connection back to direction fields, those little arrows that we drew in the direction field were actually those slopes of tangent lines. They're the same thing, just arrived at from different directions. So in your calculus case, for y equal x squared plus 1, we calculate y prime of x equal to 2x, which is the slope of the tangent line to the curve y of x. And at any point, you can plug in that x value to actually get that slope. And then you probably would have moved on to building approximations, where you could say y is approximately f of a plus f prime of a times x minus a. Or like a tangent plane approximation with multiple variables when you got to Calc 3. Hopefully you recall doing that. And so in this section, we're going to be doing Euler's method with differential equations to sort of recreate the same process that should be familiar from calculus. So Euler's method is going to use derivatives as linear approximations to the solutions of an ODE. And to get those approximations, we're going to do something really similar to what we did in that direction field. We're going to start from some point, like that star I drew on the direction field. We're going to use f of xy, that slope. Of a tangent line to some unknown y of x, and then we're going to follow that slope to recreate y of x. So the way these two things are different is in calculus you started with y, and then for some reason you went to a point and you could create the tangent line approximation to it. In this case, it went opposite direction. We have the tangent line approximations, we know what the derivative is, but we actually don't know what y is. We need some kind of fancy new integration to get it, but for now, we can just follow those tangent lines to recreate or draw the solution y that we want to see. And next up, I wanted to give you the steps to follow, and I think that's going to get a bit long, so we're going to pause here, and then in the next video, we'll open up with those steps.